Hey everyone, welcome to another lecture of the Dynamic Programming playlist. I hope you guys are doing extremely well. DP on grids is what we were doing. So, we're going to do the third problem from DP on grids, and it's going to be a slightly different problem than the couple of others that we have done in the playlist. Okay, so if you're not following the playlist, man, you're missing out on a lot of premium stuff. Please make sure you follow the playlist because you're going to learn DP in the best possible way. So, what is the problem? Today's problem will be on grids, and that's minimum path sum. So what is it saying? It's saying there's something like Ninja Land is a country in the shape of a 2D grid with n rows and m columns. Each point on the grid has some cost associated with it, right? I need to find a path from the left, which is 0 0, to the bottom right, which is n minus 1 m minus 1, and you need to minimize the sum of the cost of all numbers along the path. You need to tell the minimum sum of that path. So this question was actually asked to me in my Microsoft internship interview. It's an amazing question. Basically, it states if you start on from here and you're gonna go here. So basically 0 0 1 2. So if you just start on from 0 0 and you wanna reach the end, which is 0 comma 2, what is the minimal that you will take? Now there can be a lot of paths. Now when I say there will be a lot of paths, what does that signify? That basically signifies, for an example, I can say one of the paths is 5, 11, 5, 2. Remember, you're only allowed to move in the bottom or in the right. You cannot move up and all these. Only couple of directions. That's the bottom and that's the right. That's it. So basically, I can say if I move in the white box direction that I've written, the path sum will be 5 plus 11 plus 5 plus 2, which gives me 16 plus 5, 21 plus 2, 23. Now, this sum that you got, you have to minimize this. That's the question. This sum that you have got, you have to minimize it. So I can say, okay, Striver, what if I start from 5, I go to 9, I go to 5, and then I go to 2. I'm like, okay, let's add this up. 5 plus 9 plus 5 plus 2. So if I add this up, I think I get something as 21. You can try out all the other parts, and you will see that this is what is the minimal that you will get, and this is your answer. Now, how do you solve such kind of problems? Again, paths, all paths. So why not greedy? That's a very good question that might be arising. Strive, why not follow greedy? Why not follow greedy path? Again, makes sense, makes a lot of sense. Why don't you follow a greedy path? Let's understand how generically you understand that a greedy has not to be followed. So imagine I give you a grid, rather something like this. Okay, I give you a grid something like this, and I am like giving you something like, okay, I'm over here having 1 1 2, and I'm over here having a 10, and assume I'm giving you 8, assume I'm giving you 2, I'm giving you 100, and over here I'm giving you 5, over here I'm giving you something like 10. Okay, now if you start greedily from 10, greedily, you can move right or you can move down, right? So what you see is, over here either you can move to 8 or either you can move to 10, but the greediness will be like, let's move to 8 because it will give you a lesser cost path. So you will move to 8. Now when you move to 8, again there will be a couple of options. Either you move to 2 or either you move to 5. So the greedy nature of yours will say, I'll move to 2, and from 2 there is no other option. You have to move to 100, then to 2. So what you saw was you ended up taking this path, which is having 100, which is a very huge number. Thereby, the cost of the path will significantly rise, correct? But over here, if I would have followed probably this path, I think this would have been the minimal path, right? If I would have followed this path. So why did this happen? Because of uniformity. The values are not uniform. They're not saying the values will increase, or decrease. It might increase, it might decrease. So what happens is, today's decision might affect you tomorrow because of increasing, probably super increased values or super decreased values. So whenever there is something as uniformity, like whenever there is no uniformity in the values, you cannot apply a greedy nature because in future it might affect you. Got this? Thereby, in such cases, what you can do is, you can be like, okay, what I'll do is I'll apply something as DP. But before DP, what's the step? Don't directly go to DP. What are you saying? I have to figure out the minimum possible cost path, right? So if you're looking to figure out the minimal cost path, what's the first way? Try out all paths. That's the first way. Try out all paths. And in those all paths, tell me the path, tell me the path which has minimal cost. So whenever I say all paths, what does that signify? What algorithm that says? That definitely says recursion, because recursion is something that tries out all possible paths. Correct? So what are the rules of writing recurrence relationships? Three rules that I've taught you. What are the three rules? The three rules are very simple. Express the recurrence in terms of indexes. Over here, it's a 2D grid. So express the stuff in terms of rows and columns as ij. Second, explore all paths. Explore all paths. Third, take the best, take the minimal path as the question recommends. Minimal, maximum, count, whatever. So if you follow these three steps, you can again write any possible recursion. So why don't you follow these three paths? So can I say I'll try to write a recursion where ij will mean, if I'm doing a grid, if I'm again doing a grid and this position is ij will mean this is I and this is j. Ij will mean the minimal cost in order to reach from here to here. The minimal cost in order to reach from 0, 0 to ij is what your recursion should give me. So if I ask f of n minus 1, m minus 1, it will give me the cost from 0, 0 to n minus 1 and m minus 1, and that is what you require. Correct? So let's quickly write down the recurrence relationship. So can I say I'll write f of I comma j? I definitely can write f of I comma j. And what's your base case? Can I say the base case is quite simple, similar to the previous question that we did? If we reach our destination, yes, if we reach our destination, we can say that, okay, we have reached our destination. Let's return the value stored at a of 0, 0, because this is going to be a part of my path. Let's understand. This guy will be a part of your path, don't you think? So why don't you return this? Because this has to be added to the path, correct? And what about the other stuffs? You know, this will be I lesser than 0 or j lesser than 0. Assuming your recursion is moving in all the paths, moves out of the boundary, moves left of the boundary, similar. So what will you return? You will try to return something so that the answer is not, this path is not taken into consideration. Remember, if you are starting from here, I'll take the red pen. If you're starting from here, you moved up, you moved up, you moved up, you moved up. And this is out of boundary. This is out of grid. But you don't want this to be added. This has to return something such that this path summation is not considered. This has to return something such that this path summation is not considered. So what will you return? Generically, remember, if you're trying to find minimum paths, you'll try to return such a big value, such that when you add this big value, the path gets a maximum cost. And you never take this. Got it? So I've written the base cases. Step 1 is done of expressing in terms of indexes and writing the base cases. What's the next step? The next step is very simple. If I go upwards or if I go leftwards. Now, can I say if I go upwards, the current element is what I'm saying, okay, this will be a part of my path. The current element ij, I'm saying ij, you will be a part of my path, but I'll go up and I'll figure out how to reach from here to here. That's what we mean by up. Let's understand what do you mean by up. So imagine this is your grid and assume you are standing over here and this is your grid. So if you're saying I'll take this and I'll move here, that means you have to move from now here to here. So this portion you have to solve. This portion you have to solve. So this is what you have taken. So you'll be like, okay. So I'll be like, okay, I'll take array of a of j and I'll have to go up. So if I have to go up, from there I have to find out till 0 what is the minimal cost. Similarly, if I'm going left, I will have to take a of ij and I will have to go to the left, and from there, like if I go left, same thing, see, if I go somewhere from left, I know this portion will be there, but from here to here, this matrix, I have to figure out what is the minimal path from here to here. I have to figure out. That's what this recursion does. Recursion does that for you, correct? So at the end of the day, so again, step 2 is done, which is exploring all the paths. What's the next? Take the minimal of both of them. Take the minimal of both of them. So what are you waiting for? Take the minimal of the upward and the leftward, correct? The upward and the leftward. So that's it. So this is the upward and the leftward. Again, why upward? Because you're moving from the bottom to 0 0. You're not moving from 0 0 till the bottom. Again, why are you moving upward? Because you're solving the question in the reverse fashion. The question stated in the right and the down, so you're doing it in the opposite fashion, thereby up and left. Similar, like you're moving from the bottom to the top. Again, the prerequisites are the DP 8 lecture. That's the first lecture of the grid. If you have not seen that, please go back and watch it. Okay, so we have seen in the previous lecture, like in the lecture 8. So please follow the playlist. We have seen in the lecture 8 that if the recursion is something like we're moving in the up and left, there will be overlapping sub problems. And if there will be overlapping sub problems, what can we apply? Memoization, correct. We can apply something as memoization. So how do you apply memoization? Again, very simple trick. Very simple trick. The rule to apply, or should I show you some overlapping subproblems? I think doesn't make sense because I've already shown you whenever we did up and left, there were problems which were overlapping. So you can easily do that. So we have to apply memoization. Again, on what? Ij. So what's the value of ij? The maximum value is n minus 1 and m minus 1. So there will be a dp of n and m. Declare as minus 1. So declare it as minus 1. After that, right before the result, store it and return. And before calling the recursion, if that state has been previously visited, why don't you return that visited state? Yes, why don't you return that visited state? Step 3, step 1, step 2, step 3, and step 1 is the declaration. So memoization has been done, and once you have done the memoization, again the time complexity is n cross m, the space complexity is n cross m, but a recursion stack space of the path length. And what is the path length? M minus 1 plus n minus 1. Again, previous lectures, guys, please watch our previous lectures. So the path length is this m minus 1 plus n minus 1. So memoization is done. What is the next step? Tabulation. We have to convert this into a tabulated solution. How do you do this? Again, quite straightforward. I have told you already. I and j, two parameters. Where are the states? From 0 to n minus 1 is what I will be. J will be from 0 to m minus 1. So if you remember the previous grid classes, very simple. I equal to 0 till n minus 1. J equal to 0 till n minus 1, m minus 1. And there will be a dp of n and m. And we know if at any moment I is equal to 0 and j is equal to 0, write down the recurrence dp of ij is equal to array of 0 0. Correct? Or else there will be up, there will be a down, sorry, left rather, and the dp of I j will take the minimal of up, comma, rather not down, left, else is completed, for loop is completed, and you can print the answer to be dp of n minus 1 m minus 1. You see how we can easily solve dp on grids. It's so simple. Up will be very simple. Array of aj plus dp of up is I minus 1j. Similar to the previous classes, guys. This will be a of ij plus dp of I comma j minus 1. Simple. And basic stuffs will be if I has to be greater than 0, if j has to be greater than 0. Just make sure you do the stuff, because if I is not greater than 0, then this portion will not be there. If j is not greater than 0, then this portion will not be there. So make sure you add this guy if and if only I is greater than 0. Make sure you add this guy if and if j is greater than 0. Otherwise, it will just be these guys. So every one of you knows this now. Perfect, perfect. So that's how we can easily do this stuff. Now, since we have done it in the tabulated form, how do you do space optimization? I think I've taught you in the previous lecture how to do space optimization. Very, very simple. You know, you are at the zeroth row. First, I is 0 when you compute the first row. Then I goes to 1 when you compute the next row. Then I goes to 2, you compute the next row. I goes to 3, you compute the next row. And every time what you require is either dp of I minus 1j or dp of I of j minus 1. So this is nothing but the current row, and this is nothing but the previous row. So just carry the previous row and the current row. I've already taught you this in the lecture 8 of the grids. How do you do this? I've already taught you this. I'm not teaching you over here. I was just teaching you how the recurrence will change if the question is slightly tweaked. So I'm not explaining in depth because it's an extension. It's an extension of the playlist. So I'm assuming you watched the lecture 8 completely. On that sole basis, I'm just going on writing the recurrence relationships because it's more or less the extension of those problems, minor changes. So what I can do is I can definitely say n is grid dot size. Just start with, just make sure this is, yeah, fine. So m is definitely a grid of 0 dot size. Perfect. That's n and m. So can I say the answer initially will be written f of n minus 1, m minus 1, and definitely grid. Again, definitely I can say this. Over here I can write int f, int I, int j, and I can say vector of int grid. I can. Can I say if I is at any moment 0 and j is at any moment 0, I can return something as grid of ij. I can. If I is going lesser than 0 or j is going lesser than 0, at the same moment I can return something like int max or probably a bigger number like 1 in I. Perfect. I can say I'll go up, which means I'll take grid of ij plus f of I minus 1j grid. I can say I will go left, which means I can take grid of ij plus f of I comma j minus 1 comma grid. I can. And what I can return is the minimal of left comma up. Done. So if I just quickly run this up, you'll see everything is running, but I'll not submit it because we need to memorize it. Otherwise, we know we will get something as a TLE. So how do you memorize? Again, very simple. This is how you memorize. Declare the DP, pass the DP, just copy paste, and this time this will be DP. Pass the DP here, pass the DP here. That's the first step. Declare and pass it. Next step, initialize whatever answer you're storing. Next step, if the same state is called, return this DP of ij. Done. And I think that should be it. If I run this, it will be working fine. It does. Let's submit this. It is indeed giving me a correct answer. Okay, so the recursion and memoration does work. What about the tabulation? Again, we know the tabulation is quite similar. So we'll be like dp of n, vector of int, m, comma minus. Instead of minus 1, you can put a 0. Now, what are the states? We know the states are very simple. I equal to 0, I lesser than n, I plus plus, correct? Over here, what are the states? I j equal to 0, j lesser than m, j plus plus. What is the next? If I is equal to 0, j is equal to 0, I can say dp of ij is equal to grid of ij. Perfect. Now, can I say one thing? In else, there will be a path which will be initially, let's assume grid of ij. There will be a left path which is initially grid of ij taking current, but the up path, if the I is greater than 0, then the up will be adding something like dp of the previous guy. But if I is not greater than 0, you remember there's a base case. If it's not greater than 0, then you return something maximum. So that this path is neglected. Similarly, can you do for the left? Yes, we can. if the j is greater than 0, we say left path will be taking dp of I of the previous guy, the left guy, or else the left will be taking no path. That's it, simple as that. So in this way, I can easily find out the left as well as the up. So once I have figured out the left as well as the up, I know dp of ij will be minimum of the left or the up paths, right? And once I've done this, I know the answer will be at dp of n minus 1 and m minus 1. So once I've done this, I can definitely return this, right? Yeah, it works fine. Let's submit this code super quick. Runs fine. So next step, space optimization, which no one does. Let's analyze. So whenever there is something like I minus 1, what am I saying? I'm requiring the previous row. Yes, I'm requiring the previous row. And another dp over here is dp of j minus 1. I means the current row. dp of I means current row's previous column. So I require the previous row's j column. This means, let's understand. This means requiring previous row's j column. This means current row's j minus 1 column is what I require. So what if instead of dp of I, like the current row, I can store the current row, something like vector of int, the current row, what if I store it? Okay, makes sense. So can I say the current row is this? Say I'll take from cur's j minus 1. Absolutely makes sense. And over here I can say cur of j because the current is this. Sorry, over here I can say cur of j. Right? Nice. But what about this? dp of ij, I minus 1j. For this I require the previous. So probably to start off with, I can say there is no previous. So initially it will be everything 0. So I can say over here, this is the previous guy. Perfect. Yeah, makes sense. So we have taken the previous rows j column. I have taken the current rows. And over here we can compute the current like this. The current will be computing. So once the entire current has been computed, the value of I will increase in the next step. The value of I will go to the next. And for that next, this current which has been computed will become previous. So yeah, just do it. Previous will be current now. And at the end of the day, n minus 1 means if whenever this for loop ends, I's value will end up at n. This for loop will end when I is equal to n. So for I equal to n, who will be the previous? N minus 1. So just write in. And if I just submit this, it will be running. Space optimization is very easy. See, correct answer. Submit. It will be accepted. Check this out. Accepted. As simple as it can get. So it's not tough to space optimize. There's only a trick. Whenever you see I minus 1 or something like that, you try to space optimize. And it's very simple. Store the previous row, use it, store it again, use it, store it again, use it, store it again, use it. That's how you will beat away, right? So yeah, I hope I was able to make you understand the third problem on the grids. So just in case I did, please make sure you like it. And to follow our tradition, you can definitely comment understood under the comment section or US so that I get to know you have understood the entire lecture. And yes, with this, by the way, if you're new to this channel, you can definitely consider subscribing to us. And with this, I'll be wrapping up this lecture. Let's meet in the next one. Till then, bye-bye. Take care.
Whenever your heart is broken, don't ever